Let me introduce a new good friend in our Sturm-Liouville analysis, which is the Rayleigh quotient. The Rayleigh quotient is a method to estimate the leading eigenvalue of a Sturm-Liouville problem. Remember, the eigenvalues, we call them lambda 1, lambda 2, lambda 3, and so on, lambda n. And the very first one, the lambda 1, only that one, we can estimate using the Rayleigh quotient. And this is useful because if we can show that the first one is positive, everybody else is also positive, and the system is stable. If, however, the first eigenvalue is negative, the system is unstable, and this means, for example, it can break down. The physical system described by the PDE can break down, like it happens for collapsing bridges or collapsing buildings. This has to do with the first eigenvalue of the corresponding Sturm-Liouville problem being negative. So it is rather important to control these eigenvalues. To do this, I go back to the very general case. So here we go. Yeah, theorem 4.7. So we assume phi n lambda n is an eigenpair. Okay, so then they together solve the Sturm-Liouville problem as written here. And then lambda n can be calculated by the Rayleigh quotient, which is this absolutely super fancy integral. Now I would really like to go through the proof of this lambda n formula, and let me do this on an extra page. I write down the Sturm-Liouville problem again. P phi prime prime plus q plus lambda sigma phi is 0. Okay? And now I assume that lambda n phi n is an eigenpair, and I multiply the Sturm-Liouville problem with phi n. So then I get phi n multiplied to p phi n prime prime plus q plus lambda sigma phi n square is 0. And now we integrate this. If we integrate this from a to b, then the first one becomes, an integral from a to b, phi n, p phi n prime prime dx, plus an integral from a to b, q plus lambda sigma, phi n square dx is equal to 0. Good, okay. Now the first one we can do an integration by parts, right? You see here, maybe so you can call this u, and you can then call this dv, and then we do integration by parts for this first bit. So then this is minus the integral from a to b. So we move the derivative to the first term, phi n prime. We integrate the second term, p phi n prime, and then this one prime is gone, dx. But we have the boundary term, which is phi n, p phi n prime, evaluated between a and b. So that was integration by parts. And then the other part, I just write this to be integral from a to b, q phi n square dx. I make this into two integrals, and then we have lambda n integral from a to b, sigma phi n square dx. And then all this is equal to 0. Okay, so this lambda is a lambda n. All right. So we're almost there because we can isolate lambda n from this. So then lambda n, okay, so then we have to move the first term all to the right-hand side. Let's start with the boundary term. So phi n p phi n prime between a and b. And then plus the integral from a to b, we get the p with the phi n prime square. And then the q is from there, q phi n square all dx. And then we need to divide by whatever multiplies the lambda n, and that is the integral from a to b, phi n square sigma dx. I have to flip back to the other page to show you that this is indeed the Rayleigh quotient, but this is the Rayleigh quotient. And we also call this with a curly r of the function phi n. So the Rayleigh quotient of phi n is the eigenvalue lambda n. And so we derive this formula right there. I was concerned of the case when the eigenvalue is positive, because positive means stability. Positivity is good. And then here in corollary 4.1, we have a characterization. So if the boundary term, which shows up in the Rayleigh quotient, is positive, or actually larger or equal 0, and if the q is less or equal 0, then the eigenvalue is positive. Let's just have a quick look at the Rayleigh quotient and see how this shows up. Here it is. Okay, so let's assume this term here with the minus sign included is larger or equal 0. That was one condition. And then the q, which shows up here, if this is less or equal 0, then with the minus sign, the whole thing becomes larger or equal 0. And this means the entire fraction here is larger or equal 0. So that's a good case. Actually, what we can do even more, and this is really funny, you can sub any function here. You can just sub a different function u prime, u square, u prime square, u square in there. And then you get the Rayleigh quotient for a given function. Then we call this the Rayleigh coefficient of u. Okay, so here now we subbed in the u's instead of the phi's. This all makes a lot of sense. And we want to do this if for u which satisfies the boundary conditions. Then we come to the next theorem, 4.8, which basically says if you take u which satisfies the boundary condition and you find all these integrals, all these Rayleigh quotients for these u, then the minimum of those is the first eigenvalue or the leading eigenvalue. Okay, that's a little miracle here. So the first one, the smallest one, will be the minimum of all possible combinations of R of u. And this is simply amazing. A proof for this can be found in the book of Haberman. I rather do an example here where we study this. So we want to find the upper and lower estimate for the leading eigenvalue of a regular Sturm-Liouville problem. 2 phi double prime plus lambda phi is 0 on the interval from 0 to L with homogeneous Neumann boundary conditions. Phi prime at 0 is 0 and phi prime at L is 0. So let's identify the terms of the Sturm-Liouville problem. So the p function is 2, the q function is 0, and the sigma function is 1. So this is all very, very simple. And let's remember what the Rayleigh quotient is. So lambda n was minus p phi prime between a and b plus integral from a to b. P goes with phi prime square and minus q goes with phi square dx, and then divided by the integral from a to b phi square sigma dx. Hey, aren't you proud that I know the formula already? Anyways, so for the boundary term, this is now written here. The interval AB is now the interval from 0 to L. The P is just 2, shown up here and there. And so we get minus 2 phi at L, phi prime at L, plus 2 phi at 0, phi prime at 0. And now the prime things are 0 from the boundary condition, right? So everything is 0. So meaning in our Rayleigh quotient here, if I just go there with a different color, this guy is actually already 0. And we only need to worry about the integrals. I can also identify this to be the 2. The q is also 0. Oh, nice. And the sigma is equal to 1. Okay, my image here gets busy, but the formula gets simpler. Okay, so we have the p phi prime square term. The q term is also gone. And we have the denominator. So let's see what this makes to the Rayleigh quotient. Right, so then the Rayleigh quotient is right here. It is 2 phi prime square divided by integral of phi square. And this is definitely larger or equal 0. So then we know that a lower estimate is 0, right? So the leading eigenvalue is larger or equal 0. Yoo-hoo! Now let's use the other property. So if I choose any other function which satisfies the boundary condition, then the true value is smaller. Okay, the true value is a minimum of all the R of u's. So if I compute one R of u, it will be larger or equal. So I take the function u of x is equal to 5. This is not a solution of the equation, but it satisfies the boundary conditions because u prime is 0. So u prime at 0 is 0, u prime at L is 0. So I can take this function and sub it into the Rayleigh quotient from up here. Yeah, of course, then I get 2 times 0 because the derivative of u is 0 divided by 25, and this is equal to 0. So then this implies that for this test function, the Rayleigh quotient will be larger than lambda 1. Okay? But this guy is 0. So then 0 is larger or equal lambda 1. And here we found lambda 1 is larger or equal 0. So then together, there is lambda 1 is 0. Look what we had to do to get this result. We computed the Rayleigh quotient, which turned out to be rather easy. And we subbed in one test function, and then we computed the leading eigenvalue already. So that's actually a quite a cool method, quite efficient method to estimate the leading eigenvalue.